This is for the thesis on enriching model-driven generation of enterprise information systems with ontologies. In model-driven software engineering, models are a core part of the development process. Model transformation entails transforming an input model to either another model or to source code. This process can also be referred to as model-driven generation. Doing this ensures consistency, since the output is obtained directly from the model itself, and also reduces development time because a good amount of code is generated, for example. With model-driven generation, the generated artifacts are based on the models used as inputs. However, if two different people, have models with semantically similar concepts but they are defined differently, this will be generated as they are defined, so it will be unique to each person. Hence, the ability to share or reuse information is not fully exploited by this approach. The goal of this thesis is to enrich a model-driven generation process by introducing ontologies. Ontologies provide globally unique concepts, and if these are used in an input model, we create a common representation for the terms with the same meaning. So the generated outputs will reflect this change, and we end up with outputs that is no longer restricted to local use. Ontologies describe objects in a domain, its properties, and relationships with other objects. They do this by providing terminology for describing a domain. In model-driven generation, ontologies can be used to help developers understand the terminology they are using, to document relationships between concepts, and to create a shared understanding among different parties. Using ontologies makes it possible to describe a domain with concepts that have unique identifiers. And because of these unique identifiers, if a concept is used, the definition and information about it can be identified globally. To show the use of ontologies in model-driven generation, we enhance the generation process of MultiGem. MultiGem is a model-driven generation for enterprise management, and it generates large components of data-driven business applications. Since MultiGem is model-driven, it creates implementation specific to the domain. Here we see the input models for MultiGem, the generator itself, and the generated outputs. So it works the same way as seen previously. Input models are given to the generator and then outputs is generated. As previously mentioned, with MultiGem, the generated output is specific to the input model. This output is unique to the domain and it is used locally. So if concepts with the same meaning are represented by different terms in the input models, different implementations will be generated from them, despite their similarity. In this situation, interoperability is not fully realized because the output is dependent on the locally defined models. This is where we introduce ontologies because they are more diverse and they could provide a common representation for semantically similar concepts. Here we have an overview of the situation. Developer A has her models that she passes through to the generator. And what is generated is the sample data with 3 elements: flight, pilot, and capacity, with their 3 values. Developer B also passes his models through to the generator, and what is generated is airline, captain, and seats based on developer B's models. Assuming developer A and B meant the same thing when they said pilot and capacity, and they also meant the same thing when they said capacity and seats. Because these are defined differently by the developers, they will be generated as they are defined. So there's no way of knowing if pilot is the same as captain. There's no interoperability between developer A and developer B. And if they have operations that use pilots, they can't even be shared with developer B's operations that use captain, because they're not inherently, there's no connection between both of them. So what we would like to do is introduce ontologies. This time, developer A passes her models onto the generator, but also includes ontology references. Developer B also does the same thing with the same ontology references. And this time, instead of pilot and captain, what will be generated is EX pilot and EX pilots. So the same thing because of the same ontology. And same for capacity and seats. What will be generated instead of capacity and seats will be EQP number of seats, representing the same concepts because they both mean the same thing. So introducing the ontology references to the generator will create these elements that are represented by the same ontology concept. This will then provide a common representation, and they could be shared or reused as long as it's the same ontology concept. And these ontologies also have global identifiers, so you can always be linked and always be found. To show the workflow used in the thesis, we begin with the input model in Montegem, which is defined using CD4A. CD4A is a textual language for describing a domain, and we have an example domain here with two classes, airport and plane. Airport has the four attributes: name, airport code, country, and city, while plane has the three attributes: model, capacity, and manufacturer. We have to find a suitable ontology for the classes and their attributes. So as an example, we found this ontology NAS airport from the Atmonto ontology. This was found for the class airport itself. It has this URI, this namespace, reference, prefix, and compact URI. Another example is shown for the attribute capacity in plane. This ontology is found to represent that attribute. This is EQP number of seats, also from the same Atmonto ontology, and it has the same values: URI, namespace, reference, prefix, and compact URI. With one thing to note is that with ontology properties, they also have ranges which represent the expected value for that property. So this can be seen as data types in Java. And this particular ontology property has the range integer. So it's expecting values of type integer. After the domain model has been defined, we use tagging to introduce the ontology information. We use the tagging language for DSLs defined by Greifenberg and co-authors, also in the Montego family. This requires a tag schema and a tag model. Here we see a tag schema, which defines tags we use to introduce ontology information to the domain model. As an example, line 4 defines the tag type ontology, which takes a string value and can be used for classes and attributes. This will represent the ontology for the classes and the attributes. Additionally, we have the tag types range, which takes a string value and is used for attributes because only attributes have ranges. URI, which is the unique resource identifier for the ontology, so also will be used on classes and attributes. Range URI, which is the range, or the URI of the range for attributes alone. And the last tag type is ontology type, which just represents which type of ontology we have. So is it a class? Is it an object property? An object property is a property whose type is not a primitive data type. So this can be thought of as object properties in Java. And a and an our data type property. These are the properties which their types or their ranges are primitive data types, so like integer, float, and so on. Also used for classes and attributes. So we use those tag types we just defined in a tag model. This tag model shows how the airport class from the CD4A input model and its attributes are tagged with their ontologies. So as we see, we tag the airport class with the ontology NAS airports. We tag the attribute name in the airport class with this ontology NAS airport name. We tag the attribute airport code in the class with the ontology NAS IAC airport code, and so on. Then, after the domain model and the tagging are defined, the new generation process produces classes for each ontology. We see a generated class for the ontology NAS airports, and also these generated attributes that were all defined in the tag model just shown. Additionally, we introduced the attribute URI, which was also done in the tag model, and it's the URI for this ontology NAS airports, and another attribute ID. What is shown is a default constructor. It was mentioned earlier that the ontology class is generated with methods such as getters and setters, among others, and some other methods as well, including constructors. So this is just a sample constructor shown. In addition to the generated ontology class shown on the previous slide, we also generate methods in the ontology class such as the getters and setters, data access objects DAOs, which represent the connections to the database, data transfer objects DTOs for communication with the database, DTO loaders, and so on for the ontology classes. This is similar to how it is currently done by Montigem. And the generator is updated to handle the newly introduced ontology information. So on the right, we see a generated ontology package, which contains the ontology classes. So NAS airports is shown here, that was just shown previously, as well as other classes, ATM flight and EQP aircrafts. These are all ontologies. The ones in gray were generated for the range. So they were generated for object properties, since their types are not primitive data types but other ontology classes, and these ontology classes are also generated. With this ontology related outputs, we have concepts with global identifiers that could be used in creating an enterprise information system with globally defined concepts. A possible use case can be seen with a DTO loader that defines an operation on a particular ontology class. If another party has a similar idea and wants to make use of the same operation, they could reuse this DTO loader as long as the ontology concepts are the same. Ontologies also support reasoning and inference, which is when new relationship or new information is inferred from what we currently have. With this, new associations or new attributes or even new classes could be discovered. This brings me to the end of my presentation. To summarize, we introduced ontologies to the model-driven generation process of Montigem to have globally unique concepts. To have globally unique concepts, we updated the generator to retrieve the ontology information we added using the tag model and tag schema. This then generated ontology-related outputs. So the ontology classes, the methods in the classes, DAOs, DTOs, and DTO loaders, among others. And from this, we improve on interoperability and make it easier to reuse the outputs of the generator. Thank you.